Hello, everyone. So I just wanted to take some time to talk about price setting power, as we didn't have as much time to talk about it at the end of class as I would have liked. And so hence this video. So we're going to talk here about price setting power and think about what happens when Ayanda is the first mover. When she has price setting power, she can control the price, which is the ratio at which the two goods are exchanged. Now, importantly, she cannot control the quantity that gets exchanged at that price. All that she's able to do is to stipulate a price, and then Biko can respond to that price. So when we think about this, Ayanda has to offer Biko a price that will satisfy his incentive compatibility constraint. This requires that she must provide incentives that make the second mover's best response to act in a way that allows her to maximize her utility and get an allocation that she most wants. Okay, so what she then has to think about is to find this incentive compatibility constraint, she's finding his best response function. And she's finding his best response function to every potential price she could offer him. Here we want to think about price being a strategy that she can adopt, and his response being his utility maximizing choice given that price. So for each price, the incentive, the first mover offers, the second mover has a utility maximizing best response. Now remember, when we find that utility maximizing best response, what we're saying is that Biko is setting his marginal rate of substitution from his preferences equal to the marginal rate of transformation, which is going to be the price ratio that Ayanda offers him. So a sequential game, what does that mean? Ayanda moves first, Biko moves second. So what is she optimizing? She's optimizing her utility function subject to what? To the constraint of his best response function or the incentive compatibility constraint. What's our solution concept? It's backward induction. So if you think about really basic sequential games that you would have learned about before, what you have to think about here is you project forward into the future, you think about what the other player will do in response to you, you then move backward to work out what your optimal strategy is here. And the optimal strategy in this case is the price that she's selecting to offer to Biko. So the first mover is going to move in two steps. She's going to determine the feasible set by deriving Biko's best response function. And she's going to find the point in the feasible set that she, as the first mover, values most. What that means is she's going to think about his best response function, then find her highest indifference curve that is tangent to his best response function. This is a basic idea of, again, MRS equals MRT. She's going to take her preferences, her indifference curves representing her preferences. She's going to find the marginal rate of substitution from that, and then she's going to set that equal to the slope of his best response function, where we're going to think that is going to be giving us the marginal rate of transformation. Okay, so what is Biko's budget constraint? Here we have a price, a rate at which we're going to be exchanging the goods, and we have the amount of X that he has and the amount of Y that he has at a given allocation. Now, what we're going to say is that it has to be the case that at this final allocation, the price is going to be one such that the amount that he has is going to be equal to what he had at his endowment point. Okay, so what we'll see here is the price is going to allow him to get some, to have some X and some Y at that final point, and we have to contrast this with what he had at his endowment point. Now, an important thing to notice here is that you're probably remembering from first year that when we think about a budget constraint, it looked like that, Px times X plus Py times Y. Now, what we're assuming here is that Y is what we call a numeraire good. And as a numeraire, we're basically just saying Y is like money. So data in this case is like money. And we just set its price equal to 1. So when we're thinking about a price ratio in terms of the exchange of the goods, what we can allow here is basically a situation in which the number of X that is exchanged for Y or the number of Y that's exchanged for X, that's simply going to be the price that we end up with. And we're going to see how that works now in a second. Okay, so what do? We can take this first line here, we can rearrange it, and that's going to give us P times X minus XZB. Remember, XZB is how much X Biko has to start off with. And we're going to see that that's going to be equal to YB minus YZB. Okay, then we can rearrange that, and we can see that the amount of Y that Biko started off with here, minus how much he gives up, right? So this over here is how much he sells. He sells some Y. And then he gets some X. Okay, so he sells some Y to get some X, and that is going to be equal to the price. So that's all that we're thinking of with the price here. The price is telling us he's going to get rid of some Y to get some X. That's what this price is telling us. So the price P is the amount of data that he gives up, and it's divided by, or the ratio to, the amount of coffee that he gets. All right, so we're going to find Biko's best response to a given price. We're going to draw a price line through point Z, indicating each giving up some amount of the goods, and the price is the amount of data that Biko gives up per unit of coffee that he gets at that price. So ignore that additional word price there. So if we have point Z over here, right, and that we draw some line, right? So imagine we had some line, and I'm not even going to be thinking about some utility maximizing point here, but imagine we choose some other point on that line. I'm going to choose that, call that point B, right? Now, if it's the case that with this price line, which has a slope there, so that's P, and then the slope is equal to minus P of that line, what this means is if we're thinking about the difference between these points, between B and Z, what do we see here? He gives up some Y given up, and what does he get in response? He gets some X received. Okay, so given up Y to get some X. So whenever we think about comparing 2 points in the Edgeworth box, one endowment point, point Z, compared to a post-exchange allocation like point B, then we can say he's given up some Y in order to get some X, right? And that's the movement between those 2 points. And the price ratio P along the line, all that's telling us is the rate at which those two things are exchanged. How much Y he's given up in order to get some X. That's what our price is. Okay, so let's keep that in mind. Here what we're saying is we've got some allocation Z, which is the endowment point, and then we have a price line P4, okay, so P4 over here. And when we think about that price line, P4, how is Biko going to choose the point that he would want given that price that Ayanda offers him? Well, let's look at his indifference curves. We've got the first indifference curve, UZB, through point Z, right? That's his initial indifference curve. He can increase his utility. He can get more utility by moving to U2B. U2B is tangent to the price line at point B4. Now, what is happening there at point B4? At point B4, he is giving up some Y, okay, gives up data, that's Y, the amount of Y that he gives up, in order to get some coffee. But also what's happening at point B4 is that we have MRS equal to MRT. The MRS is the negative of the slope of his indifference curve, and then MRT is the negative of the slope of the constraint. Here the constraint is the price line. So MRS equals MRT at point B4. The slope of the indifference curve equals the slope of the price line. Okay, so that's what we see there at one point, point B4. So for one price, we find the utility maximizing combination of X and Y for Biko, and then we're therefore finding the ratio of exchange. And that's saying he is maximizing his utility at that point. Now that's only for one price. The thing is in that in order to find the best response function, we have to think about every single price that he might be charged and what his best response would be. And so what we're going to see here is, I'm just going to skip ahead, is I've got 3 different prices here. I've got P4, I've got P3, and I've got P2. These are 3 different prices. And with these different prices, what we have to see is, crucially, they all go through point Z. Why? We have to think about a movement from allocation Z to an alternative allocation. We have to think about a movement between those points. He's got to exchange from his endowment to get to another point. Okay. Now, what else is happening? If we compare the different points, we've got B4, B3, and B2. What can we see is happening at all of those? At all of those points, we have MRS equals MRT. Biko is maximizing his utility subject to the constraint of the price. So at each of those points, we have an indifference curve tangent to the price line. We have the indifference curve tangent to the price line. We have the indifference curve tangent to the price line. So at B3, B4, B2, at each of those points, we have MRS equals to MRT, and we have some level of Y given up to get some amount of X for that price. Now, when we combine every single point where he is maximizing his utility, what do we find? We find the best response function or incentive compatibility constraint. So points B and 2 would derive the same way that we derived point B4 from MRS equals MRT. Where we have all of them put together, we get the best response function. Okay, now I'm going to ask you to answer these questions by yourself. And so the first point is point Z on Biko's best response function? Yes or no? Describe the trade that would take place at the price P2. Who exchanges how much of what with whom? Are the points on the dark blue line, the best response function, below the endowment allocation on B's best response function? What do they mean? Who would trade what for what at those points? Okay, so if we think about B2, B3, B4, who is trading what for what at those different points? So think about how you would go about answering those questions. Okay, now, having established the best response function, we want to determine the final allocation that Ayanda would like to implement by finding the point in the feasible set that is associated with the highest utility. So how is she going to do that? We're going to again use the MRS equals MRT rule and select the point N for Nash equilibrium, with the associated utility UNA, where her indifference curve is tangent to Biko's best response function. So just as a reminder, when we think about the Edgeworth box, we have many indifference curves for Ayanda in the Edgeworth box. And it's better for Ayanda as we move higher up or more to the northeast in the Edgeworth box for her. Okay, so when we're thinking about that, she wants higher utility. So we can think about this U1, U2, U3, U4, and so on. So we have to keep that intuition in mind when thinking about her trying to maximize her utility subject to his best response function. So let's think about this in the following way. What we have here now is the best response function that we had from the previous figure, but we also have three indifference curves for Ayanda. We have indifference curve UZA over here, we have UWA over here, and UAN over there. Now, these are all three increasing. So UNA has higher utility than UWA, UZA has lower utility than the other two. What we can see is that at point N, what happens? We have MRS, so the negative slope of her indifference curves, are equal to the MRT, the negative slope of the constraint, or the negative slope of the best response function. So this best response function over here is giving us the MRT. So MRS equals MRT. So when we find that point of tangency, that's where we're finding her utility maximizing combination. And point N is the point that she would implement. Now, what you can then do is you can then also find how much of the goods are going to be exchanged. So if we compare point Z and point N, we can see that the amount of Y that B is going to give up is this distance here. Okay, so that's the amount of Y that B is going to exchange with Ayanda. Then how much X does he get? He gets that much X. Okay, that's the change in X that we're going to see. So there's some change in X and some change in Y. He's going to sell some Y in order to get some X at the price that is proposed to him by Ayanda. Now, I asked you some other questions here. So explain why allocation W is not a Nash equilibrium. Who could do better? So think there about who could do better when we think about point W. Why would that not be a Nash equilibrium in this game? Okay. So the final thing I want to bring up here is I want to compare the outcomes in this game versus what we would have seen in the take it or leave it power game. And the important thing here is to think about whether the outcome from this interaction is Pareto efficient or not. And so the first thing to notice is that when we look at point N, what we also see is that we have an intersection rather than a tangency of the indifference curves for the two players at point N. So Biko's indifference curve is not tangent to Ayanda's indifference curve at point N. Instead, they intersect each other. Because they intersect each other, their marginal rates of substitution are not equal at point N. Because their marginal rates of substitution are not equal, we can see that there is a Pareto improving lens when we think about point N, and we can think that there are these other points that are mutually beneficial that they're unable to agree to get to. All right, so they're not able to agree to get to there because of the structure of the game. So because Ayanda has first mover advantage, but basically acts as the first mover and can propose the price, and then Biko responds to that price. That's like kind of what's constraining them in terms of the institutions of the game. When that happens, they end up at point N. Point N is not Pareto efficient because there exist alternative Pareto superior points to point N, right? And as a result, we see that unlike in take it or leave it power, the outcome of the interaction with price setting power is Pareto inefficient. So just a reminder, what are we seeing here? The allocations from take it or leave it power, TA and TB, those ones are Pareto efficient because the players' marginal rates of substitution are equal. When we look at point N, the Nash equilibrium of the price setting game, when Ayanda has price setting power and Biko does not, what do we see there? The outcome is not Pareto efficient because the players' marginal rates of substitution are not equal. Now, the other thing that's important, though, is that if we compare the two situations in which Ayanda has take it or leave it power versus price setting power, there is some difference. The difference there is that the outcome is not as unequal as it was when Ayanda had take it or leave it power. So notice here that Biko has in fact increased his utility. He has higher utility than he would have had if Ayanda had take it or leave it power. Moreover, Ayanda has slightly lower utility at UNA than she would have had if we sketch an additional indifference curve for her there that is the indifference curve she would have been on if she had take it or leave it power. So Ayanda's utility is lower when she has price setting power compared to when she had take it or leave it power. And Biko's utility is higher than what he would have had if Ayanda had take it or leave it power. So the outcome with price setting power is less unequal, but Pareto inefficient. The outcome with take it or leave it power is very unequal, but also Pareto efficient. And we'll stop there for now.